Welcome back to The Explainer. Let's dive right into some truly fascinating aerodynamic mysteries today. Have you ever wondered what invisible forces are secretly pulling and pushing an airplane while it's up in the sky? Well, today we're stripping away all the complex math to look directly at the actual physical phenomena that make an aircraft behave the way it does. We're going to specifically look at two major forces, gyroscopic precession and P-factor. To get us started, picture this. You're watching a single-engine plane speed down a runway, or maybe climb into the sky. Did you know the pilot is actively fighting a physical tendency for the nose of that plane to just drift off to the left? Why does it always want to veer left? It's not a manufacturing defect, it's pure physics. And understanding why this happens honestly unlocks a whole new level of appreciation for flight.
Okay, let's dive into this. Here's our roadmap for today. First, the propeller as a gyroscope. Second, the rule of precession. Third, the P-factor phenomenon. Fourth, a very cool helicopter visualization. And finally, correcting the flight path.
All right, part one, the propeller as a gyroscope. So, if we want to understand what's pulling on a plane, we've got to look at that massive spinning hunk of metal right at the front of it. A rotating propeller is basically a fantastic gyroscope, and all practical applications of a gyroscope are based on two fundamental properties: rigidity in space, which is what keeps a spinning top standing upright, and precession. But for our discussion today on how an airplane moves, we are laser-focused on precession. Which brings us to part two, the rule of precession. Let's get our ground rules straight with a clear definition from our source text. Precession is the resultant action or deflection of a spinning rotor when a deflecting force is applied to its rim. Sounds a bit dense, right? What it actually means is this. If you push on a spinning disc, the reaction to that push doesn't happen where you applied it. It happens somewhere else entirely along the spin cycle.
And this brilliantly illustrates exactly what we're talking about. See that upward applied force at the bottom of the spinning disc? You'd think the physical reaction would happen right there at the bottom. No way. The resultant force actually takes effect exactly 90 degrees ahead in the direction of rotation. That little 90-degree shift, that is the rule of precession in action.
Let's apply this to a real-world scenario, a tailwheel plane taking off. We'll slow this chain reaction way down. Step 1, the pilot raises the tail off the ground to level out during the takeoff roll. Step 2, pitching the nose down like that has the exact same effect as applying a physical force to the very top of the propeller's rotation. Step 3, thanks to precession, the actual resultant force shifts 90 degrees ahead, landing on the right side of the propeller arc from the pilot's point of view. And step 4, that invisible push on the right side causes the entire aircraft to just yaw hard to the left. It's like a giant interconnected puzzle. Because of this gyroscopic action, the airframe is locked in a beautifully complex cycle. Yawing around the vertical axis creates pitching, and pitching around the lateral axis creates yawing. You pull up or push down, and suddenly the plane wants to turn left or right. It's a constant dance of physics.
Moving on to part 3, the P-factor phenomenon.
Now, precession isn't the only culprit trying to drag the plane left. We also have to deal with asymmetrical loading, which most pilots just call P-factor. This really kicks in at a high angle of attack, meaning the nose is pointed high up into the oncoming wind. To wrap our heads around P-factor, think of the propeller not as one solid disc, but as individual flying wings. The downward moving blade on the right swings down and forward into the wind. It has a higher resultant velocity, so it literally takes a bigger bite of the air, creating more thrust. Meanwhile, the upward moving blade on the left is swinging away from the wind. It gets a smaller bite and generates less thrust.
Now, what's really interesting about this slide is the stark imbalance it shows. Look on the left. At a low angle of attack, those load arrows on the blades are pretty equal. Thrust is totally balanced. But on the right, at a high angle of attack, that downward blade has a massive arrow, and the upward blade has a tiny one. The center of thrust has completely shifted to the right side of the disc. Imagine pushing a shopping cart, but you push really hard only on the right handle. The whole thing is going to veer left, right? Same exact deal here.
Let's make this even clearer in part 4, the helicopter visualization.
Visualizing wind vectors hitting spinning blades at weird angles can be honestly a bit abstract. So let's try a brilliant thought experiment straight from the source to make P-factor instantly relatable. I want you to imagine taking that airplane propeller shaft and just tilting it straight up at the sky. Mount it perfectly vertical, exactly like a helicopter rotor. Now, imagine a horizontal wind blowing steadily across it. Without that wind, both blades would have the exact same airspeed, but the wind changes everything.
Because of that horizontal wind, the blade spinning forward directly into the airflow suddenly experiences a way higher relative airspeed. It's slicing right into the wind, meaning way more thrust. The retreating blade? It loses relative airspeed and creates less thrust. Now just mentally tilt that vertical shaft back down to a shallower angle, pointing it forward until it matches a climbing airplane. That unbalanced thrust, stronger on the advancing side, it doesn't go away, it just gets proportionally smaller and only actually hits zero when the propeller is perfectly horizontal to the oncoming air.
All right, part 5, correcting the flight path.
So we've got gyroscopic precession reacting to pitch and P-factor reacting to high angles of attack. Both are literally conspiring to drag the nose left. But the crucial point is that these aren't static forces, they are incredibly dynamic. These torque effects are constantly shifting in value based on a bunch of key variables. What phase of flight are you in? Are you taking off, climbing, or cruising? What's the airframe design, engine type, propeller combination? One force might totally dominate right at takeoff, while another completely takes over during a steep climb.
And that brings us to the ultimate responsibility of the person actually sitting in the cockpit. Our source states it perfectly, quote, "To maintain positive control of the aircraft in all flight conditions, the pilot must apply the flight controls as necessary to compensate for these varying values." You see, it's not about engineering a plane that completely eliminates these forces. That is physically impossible. It's all about the pilot recognizing this invisible physics in real time and smoothly stepping on the rudder or tweaking the elevator to keep the aircraft flying straight and true. So, we've seen how just pitching the nose down shifts forces 90 degrees through precession, and how simply tilting a blade alters its grip on the air through P-factor. Which leaves us with this final thought. If a simple adjustment in angle dramatically alters the very physics of thrust, what other invisible forces is a pilot constantly negotiating up there in the sky? The atmosphere is literally a swirling ocean of physical laws, and every smooth flight you take is a testament to human engineering and pilot mastery. Thanks for joining me on this explainer today. Keep visualizing those mechanics, and I'll see you on the next one.